Hi, my name is Shizhuo and welcome to my Elec 599 presentation introduction. In this project, I focused on developing an experimental platform for quantum sensing based on spin defects in hexagonal boron nitride, or HBN. I will start by briefly introducing the background and motivation. So solid-state defect centers have become an important platform for quantum sensing and quantum information processing. Among them, the nitrogen vacuum or NV center in diamond is the most well-established system. It enables optical initialization, spin-dependent fluorescence readout, and coherent microwave control, all at room temperature. Because of these properties, NV centers can function as nanoscale probes for magnetic fields, electric fields, strain, and temperature. However, diamond is a bulk material. So this makes it difficult to integrate NV centers with low-dimensional systems or bring them very close to target samples in certain experimental configurations. This is where hexagonal boron nitride becomes interesting. HBN is a 2D van der Waals material with a wide backup. It can host optically active defects while remaining automatically thin and mechanically transferable. This allows defect centers to be placed very close to external systems, which is highly advantageous for sensing applications. In recent years, single photon emitters in HBN have been widely studied, and more importantly, optically detected magnetic resonance, which is ODMR, has been demonstrated in intrinsic speed effects in HBN at room temperature. This shows that HBN can support both optical and spin degrees of freedom, making it a promising candidate for quantum sensing. However, there is a fundamental limitation in conventional optical readout, which is spatial resolution. Even if the spin sensitivity is excellent, the optical microscope is still diffraction limited. Typically, the resolution is on the order of hundreds of nanometers. This becomes a very serious limitation when we want to resolve closely spaced emitters, study nanoscale heterogeneity, or performing sensing in dense defect ensembles. So to overcome this limitation, we turn to STAD microscopy, which stands for Stimulated Emission Depletion Microscopy. The key idea of STAD is to use a second laser beam, called the depletion beam, to suppress fluorescence everywhere except at the very center of the excitation spot. By shaping this beam into a donut profile, we can effectively shrink the emission region below the diffraction limit, achieving super resolution imaging. Importantly, STAD has already been demonstrated in solid-state systems such as NV centers, which suggests that it can be combined with defect-based quantum platforms. So this leads to the center idea of this project. We aim to build an integrated platform that combines ODMR, which provides spin sensitivity, with STAD microscopy, which provides spatial resolution. In other words, we want to achieve quantum sensing with both high sensitivity and nanoscale spatial precision. So experimentally, this requires integrating several components into a single system, including optical excitation, optical depletion, microwave control, and photon detection. So in the current stage of this project, the focus is on building the system and testing the depletion pathway. Specifically, we investigate whether a 634 nanometer laser can induce fluorescence quenching in HBN emitters, which is a necessary step toward realizing STAD. Although we do not yet observe a clear quenching effect, this result provides important information. It suggests that the system is still below the required depletion regime and highlights the need to improve factors such as laser power and the sample, or spectral overlap, or beam alignment. So in summary, this project lays on the groundwork for combining super resolution microscopy with spin-based quantum sensing in 2D material.